Hello everybody, and today I would like to talk about Fokker-Planck equations, and what is Fokker-Planck equations? Fokker-Planck equations describe the evolution of stochastic systems. I would like to remind you that by stochastic system, we mean the system which have quite random behavior. Stochastic process, quite random behavior. The mathematical. Stochastic means a random process is a mathematical object usually defined as a sequence of random variables, where the index of the sequence has interpretation of for example, let's say we try to describe the erratic motion of small particles that are immersed in fluids, and stochastic behavior, for example, exchange rates. All these things can be described by Fokker-Planck equations. And in general, Fokker-Planck equations can be applied to equilibrium and non-equilibrium systems. So they can be applied to systems that operate close to stationary states of thermal equilibrium, and to systems that operate far from thermal equilibrium. However, it is quite helpful to know this. And today we can talk specifically about topic about Brownian motions, Brownian particles, and Langevin equations. So, what is Brownian particles? Brownian motion. As you can see here, it's a random motion of particles. So it looks like this. And next, I will tell you why do we need Langevin equations. So let us consider a single particle here. You can see, yeah, a single particle, a so-called Brownian particle. There's a Brownian particle here. That is in contact with environment. So this is everything is our environment here. And in general, there are interactions between a Brownian particle, you can see here, right, and the part and its environment. So a helpful notion of the environment is a heat bath. Heat bath. Let's see here some representation. Heat bath composed of a larger number of heat bath particles. So here we have a lot of particles inside. So from this point of view, a complete description of the systems at hand requires taking the states variables of the Brownian particles. So here we have a lot of Brownian particles. And the state variables of all heat bath particles into account. So we need to know everything. In many cases, however, a reduced description can be obtained that involves only the state variables of the Brownian particles here, and the interactions between the heat bath particles and the Brownian particle then result in two forces. We have two forces that act on the Brownian particle. So two forces control the motion of this Brownian particle. The first one is a damping force. Damping force. So what is it? A damping force. Damping is influenced by the form of the system that is the effect of using the. Okay. Force. Okay, an example. Okay, fluctuation force. Fluctuation force. Fluctuation force. Let's see here an example. Fluctuations, physics, theorems. Okay, make some images. Come on, give me some further. Okay, we have two forces, and as I said before, damping force and fluctuation force that control direction of this particle, and we can describe it mathematically. Now I need to write a formula, and I need my pencil. One moment. Let's open Paint here. And I will try to explain this topic. Okay, didn't found my pencil yet. So I will write it manually by my mouse. Later, I will use some additional tools for this. We want to draw some equation. So, for example, let x t denote the state variable of the Brownian particle. This Brownian particle, we want to denote the state variable of the Brownian particle. So then the evolution of the Brownian particle may be given by this equation d t by dt. How fast this variable is changing? A small amount of time, a small amount of time. So minus x on t plus q U, and then we have gamma. Gamma on T. Yeah, so this is our equation. Let's say this. Okay, so what is it? We said let x and t denote the state variable of the Brownian particle, then the evolution of the Brownian particle may be given by this equation. So, a moment, and minus gamma xt. This part is a linear damping force. And this little thing. Okay. The gamma is a positive damping constant, and all this gamma x is a linear damping force. So this is the first part. The second part is called the function gamma t, and it describes a fluctuation force. Yeah, fluctuation force. So this is fluctuation force. Is a function that describes fluctuation force, which is only defined in a statistical sense. And Q here describes the strength of the fluctuation force. So this is the strength of fluctuation force, and since so this is the strength of our fluctuation force, and since all of this okay, Q gamma describes the impact of noise source on the Brownian particle. We also say that Q corresponds to a noise amplitude. So Q corresponds to the noise amplitude. This is our variable is about. So what's next? We'll call it this equation, and if our gamma on T in this equation describes a particular fluctuation force, namely Langevin force, which is topic of our lesson today, then this equation dx t by dt equals minus gamma xt plus O gamma is referred to as Langevin equation. So this is our Langevin equation. Yep. For statistic process or statistic processes described by Langevin equations, we can write evolution equations for the corresponding probability densities. And yeah, probability densities. Let's write something like this. Okay, I will be very accurate to do this. So this is our equation. P x t by dt. So how fast the probability density function will change equals gamma. Definitely, I will buy a little expensive. Okay, gamma p t by dt plus q, and then we have double t d double d square p x t by dt dx squared. Yeah, that's it. So let's draw it in a one small formula, right? Wait, this is our second equation. We will call it, for example, something like this. Yeah, as you can see here. So for the stochastic process given by this equation, Langevin equation, uh, for the stochastic process given by Langevin equations, which we can see here, dxt by dt equals minus gamma xt plus q gamma. The evolution equation of the probability density p reads as follows, like this: pxt by dt equals gamma pxt by x plus plus q d square pxt by dx square. And this equation, which we wrote here, is an example of linear Fokker-Planck equation. And I want to remind you that Fokker-Planck equation is a particular differential equation that describes the time evolution of the probability density function of the velocity of a particle under the influence of drag forces and random forces as Brownian motion. We say we have a fluctuation force and then force. Yeah. So like some drag forces and random forces. And stochastic processes described by linear Fokker-Planck equations, such as this equation. So stochastic processes described by linear Fokker-Planck equation, such as this equation, are called Markov diffusion processes. That's it. And maybe we can Markov diffusion processes. Okay. Diffusion process, no. What Markov diffusion process? Okay. This diffusion process is a clever continuous time process with almost continuous. Diffusion process is stochastic in nature and hence it is used to model many real-life stochastic systems, Brownian motion, Brownian motion, etc. Einstein, Unblack processes, examples, diffusion processes. It is used heavily in statistical physics, etc. Mathematical definition is quite important. The diffusion process is a Markov process with continuous sample path with simple equation with a Fokker-Planck equation. So diffusion process is a Markov process with continuous sample path for which the common forward equation is a Fokker-Planck equation. And I can remind that Markov process is a stochastic model describing a sequence of possible events in which the probability of each event depends only on the state it was before. Okay, in the previous attended to the previous event. We have some tables how we can go in between each of these states. That's it. And yeah, iterative diffusion is also important, but we will talk about this later. So simply say, I want to sum up. Now we know what is a Brownian particle. Brownian particle and Brownian motion. So it's a random motion of particles. Looks like this. We have two forces: damping force and fluctuation force, which move this particle in the environment. And also we have a Langevin equation, which looks like this, that describe a fluctuation force, Langevin force, and a quantum force. So describe the motion of the where this particle will be in next small amount of time. And that's it. So this is Langevin equation, this is our Brownian motion, Brownian particle. Now we can describe motion of this particle by using this Langevin equation. Yeah, that's it. And I want to say thank you for your attention. And next time we will talk about also about some interesting topic. However, okay, have a good time and bye bye.